In this video, I'll talk about the 0-1 knapsack problem. The 0-1 knapsack problem is a very classical combinatorial optimization problem where we are given n input items, and each item has a weight Wi and profit Pi, and all of the input numbers are non-negative integers. And the goal is to find a subset of the items that maximizes the total profit, subject to the constraint that the total weight of the items should be smaller than or equal to the capacity. And we denote the capacity by small letter t. This is an NP-hard problem, but it's known that it can be solved in pseudo-polynomial time, which means poly in n and t. And recently, there has been a lot of research on trying to determine the fine-grained complexity of 0-1 knapsack problem, that is the exact exponent on the polynomial running time complexity. Now let's look at the most basic algorithm, which is dynamic programming. It runs in order nt time. This algorithm actually computes a DP table of length t, where the wth entry of the DP table denotes the maximum achievable total profit by a subset of items with total weight equal to w. And this DP algorithm runs in n iterations. In each iteration, it updates the DP table by adding a new item, and it takes linear time to update the DP table. And alternatively, there is another algorithm that runs in roughly m plus t squared time, and we can even shave off some super polylog factors. On the lower bound side, it is known that if 0-1 knapsack can be solved in truly subquadratic time in both n and t, then some popular conjecture in fine-grained complexity will be false. More specifically, there is this max plus convolution problem where we are given two arrays of length t, and we want to compute for each integer k, what is the maximum sum of ai plus b of k minus 1, where I ranges from 0 to k. It is conjectured that this problem cannot be solved in truly subquadratic time. And we can see that this conditional lower bound of m plus t to the 2 minus delta matches both the nt time algorithm and the m plus t squared time algorithm, in the sense that under this conjecture, it's not possible to strictly improve these running times by a poly n or poly t factor. So it seems that with respect to the parameters n and t, we have a reasonably good understanding of the fine-grained complexity of the 0-1 knapsack. And more recently, there has been some research on trying to get a finer-grained understanding of the 0-1 knapsack by looking at another parameter, Wmax, which is defined as the maximum input weight. And this is particularly useful in the setting where the items could be much smaller than the capacity. And the main question along this direction is whether we can improve the n times t and n plus t squared algorithm from the previous slide to run in roughly n Wmax or n plus Wmax squared. And such improvements actually will not violate any known fine-grained conjecture, because in the proof of these conditional lower bounds, the hard instances actually have Wmax roughly equal to a constant times capacity. And we can also look at what's the running time of the textbook DP algorithm with respect to n and Wmax. Without loss of generality, we can assume that the capacity t is strictly smaller than n times Wmax, because otherwise the instance would be trivial. So the n times t time bound could be written as at most n squared times Wmax. So this is cubic in n and Wmax, while the lower bound is quadratic. So there is still a large gap between the upper bound and lower bound. Now let's look at previous algorithms for 0-1 knapsack with respect to the Wmax parameter. We can see that there were a lot of results that achieve cubic dependence on n and Wmax. In particular, this paper by Polak, Rover, and Vendrisk in STOC21 achieved n plus Wmax cubed running time. And very recently, there are 3 independent works that all improve on this time bound, and they all came out in last summer. 2 of these papers achieved running time n plus Wmax to the 2.5, and the other one achieved Wmax to the 2.4 by Chen, Lian, Mao, and Zhang. And the main result in this work is to finally improve the exponent to 2, which matches the condition lower bound based on the max plus convolution conjecture. The time bound is n plus Wmax squared, and the same result was also independently obtained by Carl Brinkmann. And it should be noted that some of the results shown on this slide actually work for the more general problem of bounded knapsack. And as another remark, all these running times can also be written alternatively as m plus pmax squared, where pmax denotes the maximum profit of the input items. This can be achieved by a known reduction that switches the role of the weight and profits in the input instances. Both our work and Brinkman's work build on the technical ideas introduced in the previous work by CLMZ, which appeared in STOC24. Now let's go into the technical part of this video. First, I'll talk about some ingredients from previous works, which will also be used in this paper. First, I'll talk about two basic ingredients which underlie this cubic time result in ICAL21. The first ingredient is proximity to the greedy solution. In the greedy solution, we sort all the input items in decreasing order of the efficiency, Pi over Wi, and we greedily take the solutions with top efficiency until the next item does not fit into the capacity anymore. And let's denote the solution obtained by the greedy solution G. And in general, this greedy solution may not be the optimal one, but we can look at the difference between the optimal solution and the greedy solution and see how close they are. Let's write the optimal solution as G minus B union A, which means we remove the items in B and add back the items in A. Then the proximity lemma from the previous work says that the total weight of the items that we add and the total weight of the items that we remove should be bounded by order W max squared. This bound was proved by the observation that the subset sums of the weights of the items in A and the subset sums of the weights of the items in B should not have any common element except the trivial one, which is 0. The reason is that if there were a pair of subsets of items in A and B that share the same weight, which is non-zero, then we can switch them, which does not affect the total weight, so that the solution stays feasible. But by the way we sorted the items in decreasing order of efficiency, we know that the efficiencies of the items in A should be lower than the efficiency of those in B, which means that this exchange will improve the total profit of the solution, which will violate the optimality assumption. Based on this proximity lemma, we can change the way that we do DP. Instead of doing DP from the empty set, we can start from the greedy solution and use DP to find the optimal way to exchange items to reach the optimal solution. Let's call the set of items A and B the exchange solution. And in the DP, we can add items that were not taken by the greedy solution. These are called positive items, and we could also remove items from the greedy solution, and this can be thought of as negative items. And if we do DP in this way, then the DP state only needs to encode the total weight difference caused by this exchange. And by the proximity bound, the DP table length becomes order W max squared instead of T. The second ingredient is batch DP updates using concave max plus convolution. Recall that in Bellman's textbook DP algorithm, we have n iteration where each iteration takes linear time in the DP table length. But actually, we can do batch DP. For each possible weight W, we can update using all the items whose weight equals W at the same time. And this can be done in time that is still linear in the length of the DP table, so that the total time complexity becomes the number of distinct weights in the input instance times the DP table length. At a high level, this is possible because inside the weight class, the optimal solution should always take the top k items, and the total profit is a concave function in k. And there was this SMOC algorithm, which can compute the max plus convolution of an arbitrary array and the concave array in linear time. So if we combine these two basic ingredients together, then we arrive at the cubic algorithm from this ICAL paper. Now let's talk about the more recent paper, which used additive combinatorics of subset sums to prove better proximity bounds. There is a theorem from additive combinatorics which says that suppose an integer set A from the range of 1 to W has size much greater than root W, then the subset sums of A must contain a length W homogeneous arithmetic progression. Here, homogeneous means that each element of this arithmetic progression is a multiple of the common difference. And moreover, it can be shown that the elements in this AP is not too large. This theorem has been used in a lot of results showing fast algorithms for various settings of the subset sum problem, where subset sum is equivalent to the special case of 0-1 knapsack where the profit equals weight. And in SODA from last year, this theorem was first applied to the knapsack problem, but the argument in that paper had some loss, so that it was only applied to the approximate version of 0-1 knapsack. And more recently, the paper by Chen, Lian, Mao, and Zhang used a very different argument and used this additive combinatorial result to solve the exact version of 0-1 knapsack faster than previous works. They proved the following lemma using the previous AP result, that A, B be multisets of integers from the range of 1 to W. If the size of the support of A is much greater than root W and the sum of the elements in B is much greater than W to the 1.5, then the sets A and B must share a non-zero common subset sum. Using this lemma, they designed a partition of the input items defined as the following. We take the greedy solution G and suppose the breakpoint is represented as this blue line. Then they go from this blue line to the right and select the first red breakpoint such that the number of distinct weights of the items between these two lines is equal to 2 times a constant times root W. And let us denote this interval by X and the interval to the right by Y. And we do a similar thing in the direction to the left. And let's consider the optimal solution and represent it as the greedy solution where the set B is removed and the set A is added back. Then, using this lemma 1, they showed the following kind of proximity bound. The total weight of the items in the interval Y intersecting A should be at most order W to the 1.5. And symmetrically, we can also have a bound on the total weight of items in Y prime intersect set B. Using this proximity bound, they can use the batch DP algorithm to obtain an algorithm that runs in W to the 2.5 time. So the algorithm first considers all the items in X and X prime, because there are only order root W max many distinct weights in this interval, and the DP table length is W max squared, as we mentioned earlier. The total time for this batch update is W to the 2.5. And then they update the items in Y and Y prime. And now using this proximity bound, the DP table length can be reduced to only order W max to the 1.5. And the number of distinct weights is at most W max, so the product is still W max to the 2.5. And in their work, they further used a more refined partitioning using the work of Breman and Wellness 21 and obtained a slightly better running time of M plus W max to the 2.4. Now let's talk about our improvement, which is a more refined implementation of this previous W max to the 2.5 algorithm. So our first improvement is pretty straightforward, and we can improve the second step of the previous algorithm to W max square time by using a dyadic partitioning, which further partitions the Y interval by choosing the number of distinct weights in the interval between the blue line and the red line to be various powers of 2 that are greater than root W. And then using a generalization of this lemma 1, which was also proved in the previous work, where the root W could be replaced by W to the P and W to the 1.5 can be replaced by W to the 2 minus P. And using this, we can make sure that the DP table length in each layer, the product of the DP table length in each layer and the number of distinct weights in that layer is roughly W max squared. So in this way, we can use batch DP to implement this step in W max square time. And the more challenging part is to improve the first step of the algorithm. So here, the number of distinct weights have been reduced to root W max, but we still need to compute a DP table of length roughly W max squared. And this part is the more technical part of our improved algorithm. So in our new algorithm, we need another structural lemma of the optimal solution. Let's first introduce a definition, which is the R support of a multiset A. This is defined as the set of items that occurs at least R times in the multiset. Then our structural lemma says that suppose we have two multisets A and B, where the elements are integers from 1 to W, and suppose the R support of A is much greater than root of W over R, and the sums of the elements of these two multisets do not differ by too much, then A and B must share a non-zero common subset sum. This was proved by using a result from Brinkman and Wellnitz, which generalized the Feynman-Sarkozy AP results to multisets, and we also used the technique from previous work. Now let's apply this structural lemma to the optimal exchange solution, where we add the set of items A to the greedy solution and remove the set B of items. And this optimal exchange solution automatically satisfies the condition that the total weight of A and B do not differ by too much. Now let's represent the set A of items using the following histogram, where each column corresponds to a possible weight, and we know that there are at most roughly root W max possible distinct weights that we care about. And for each column, the height of this column represents the number of items of weight equal to W that are included in set A. By our structural lemma, we know that suppose we draw a horizontal line at height R, then there must be at most O tilde root W max over R columns above row R. This is because if there are more columns than that, then it will mean that the R support of A is much greater than root W over R. Then we will obtain a non-zero common subset sum between A and B, which we could use an exchange argument to contradict the optimality assumption. So in this way, we have some understanding about the distribution of the heights of the columns in this histogram. Next, let's exploit this property in our algorithm. First, we need to partition the input items based on the ranks. So in each weight class, let's sort the items in descending order of the profits. For example, a rank 1 item means it is the most profitable among all the items of the same weight. And in this histogram, if the column corresponding to weight W has height H, then it means items of rank 1 through H in the weight class W are included in A. Now let's partition the input items into log W max many rank classes, where the boundary of these classes are defined using powers of 2. And let's perform batch DP in rounds, where in the ith round, we batch DP all the input items whose rank are in the interval 2 to the I minus 1 to 2 to the I. So basically, we are kind of growing the columns in this histogram. So let's say this is optimal solution. Then if we finish the first round of DP, then the partial solution represented by this histogram should be included in the DP table. And in the end of the next round, the partial solution of this histogram should be included in the DP table, and so on. So using our structural lemma, which says that the rth row of this histogram has at most root W max over R columns, then we can obtain an upper bound on the total area below this horizontal line, which can be obtained by an integral from 1 to R. So after this calculation, we know that the number of items below row R should be root of RW max, which means that the total weight of these items should be root R times W max to the 1.5. So basically, this bound is the required DP table length once we finish the DP, which grows the columns of the histogram up to the rth row. So now let's consider how to perform the DP updates. Suppose we're looking at the round where we have just finished updating all the items whose rank are below R, and in the next round we want to update using items of rank from R plus 1 to 2R. we have a current DP table, and let's further assume that inside each cell of the DP table, we also have a representation of this partial solution using the histogram, in addition to the profit to the total profit value. We know that the current DP table has length root r times W max to the 1.5 from the previous slide. And each histogram in this DP table looks like this. Now let's suppose we want to perform DP updates by adding more items to these partial solutions. And for example, we could add the next J items coming from the Wth weight class. And visually, this could be represented as growing the column corresponding to weight W by a height of J. And here, a crucial observation is that we should only grow these active columns, where the active columns are defined as those columns that touch the R horizontal line. And we can see that the inactive columns should not grow. This is because if we try to grow an inactive columns by adding more items to this partial solution, then because this column is not full height, then it means that there's actually a better set of available items that we could add with the same total weight, but actually have higher total profit. So this will contradict optimality. So basically, this means that when we are doing DP updates from a cell in the DP table, we should only grow the active columns. And by our structural lemma, the number of active columns should be at most root of W max over R. This idea of active columns is inspired by a previous work by Deng Mao and Zhong, which used this idea to show better algorithms for some variants of the unbounded knapsack problem, which is much simpler than our 0-1 setting here. So now let's consider the very ideal scenario where inside all the DP cells of the DP table, the active columns of these cells are actually the same set of active columns or active weights. Then this will mean that in total, there are only root of W max over R many active weights that we need to consider. And we can use the batch DP algorithm to update all of them in total time, the number of distinct weights times the length of the DP table. And here we can see that the root R factor in these two quantities cancel, and the total time complexity would be the product of these two quantities, which is roughly W max squared. And this is the ideal time complexity that we want. But the issue is that in reality, different cells in the DP table may have different active weights, although in each cell there are only very few of them, but the union of the active weights across all the DP cells could still be very large. And our main technical component is a very complicated algorithm that handles this issue, so that even if the union of these active weights are large, we can still do batch DP, and the time bound would still be the same as before, which only depends on the upper bound of the number of active weights inside each individual DP cell. Here, we omit all the details of this part. Let me just mention some ingredients, which include a tall matrix version of the SMOC algorithm and a skipping argument based on concavity, and also a color coding argument from Brinkman 17 subset sum algorithm. This is all I want to say about the technical part of this paper. Now let me conclude by first mentioning the independent work by Brinkman. His algorithm is different in that he obtained a more refined way to partition the items into roughly log n squared many classes and obtain an improved proximity bound than the previous work. After this partition, he only uses the standard batch DP based on concave Max-Ross convolution. So overall, his algorithm is simpler than our work. Now let me mention some open questions. First, can we achieve O tilde n times W max time for 0-1 knapsack? This would also match the conditional lower bound based on Max-Ross convolution conjecture. And currently, the best result along this direction is an n to the 1.5 times W max time algorithm by He and Xu. And a second question is, can we obtain lower order improvements? Currently, our algorithm has running time n plus W max squared times 4 log factors. Let me remark that both these open questions are already solved for the easier problem which is the unbounded knapsack problem, where each input item has infinitely many copies. Thank you for listening.